What are inverse functions? When is a function one-to-one? And what will be the domain and range of an inverse function? In this example, we have a mapping. This particular mapping represents a function, and our job is to figure out whether it is one-to-one. Yes, this function is one-to-one for this reason. Each input has exactly one output, as shown in the mapping, and each output has exactly one input. Therefore, we say that this function is one-to-one. Now, it's important when functions are one-to-one because only one-to-one functions will have inverses. This particular graph of a function, to determine if this is one-to-one, we want to consider the vertical line test and the horizontal line test. Well, because it's a function, we know that it passes the vertical line test. We can state with confidence this function is one-to-one because it passes the vertical line test. It also passes the horizontal line test. So therefore, we can say that the function whose graph is shown is one-to-one. In the next example, we have a list of ordered pairs. We're asked to find the inverse of this one-to-one function. Okay, so as you know, a function is a set of ordered pairs where each input is mapped to exactly one output. So the inverse is when we switch the inputs and the outputs. So the ordered pair -3, 5, which is a set, which is a member of the function, 5, -3 will be part of the inverse. So let's show you the inverse function. Notice what we've done. We've just switched the inputs and outputs of each ordered pair. So the domain of this inverse function are the x coordinates, so 5, 9, 2, 11, and -5. The range of the inverse function will be the y coordinates. So one of the common things that we want to do here is to verify that functions are inverses of each other by showing that f of g of x and g of f of x both equal x. So this is where your knowledge of function compositions will come in handy. Let's start by looking at f of g of x. So that is f of x over 4 plus 2. So my x over 4 plus 2, I'm going to write that in place of x in my f function. I'll distribute the 4 to both terms inside the parentheses, and I'll combine like terms, and I've just shown you that f of g of x definitely equals x. Now g of f of x, that's g of 4x minus 8. So I'm going to use 4x minus 8 and substitute that in place of x in the g function. And I'll take both terms in my numerator and divide them individually by 4, and I'll simplify this expression. And in fact, g of f of x also equals x. So what we want to do now is we want to think, is there a graphical significance of this truth that f of g of x and g of f of x both equal x? So here we have the graph of a function, f, which is given in blue. And we're asked to graph the inverse function, f inverse of x. And what we want to remember is this line, y equals x, is going to be the line of reflection between f of x and f inverse of x. Now, some people would have trouble just drawing this, sketching this freehand without some points on the graph that are significant. So what I like to do is look at a point of f of x that's already there, the 1, 2, and I want to switch the x and the y. So what I know is that 2, 1 is going to be a point in my inverse function. And then I have 1, comma 0, which will also be on my inverse function. Now my next point, negative 1, 0, I'll switch the input and output. And that last point, negative 2, comma negative 2, when I switch the input and output, it's the same point, right? So what we're going to do is we're going to graph these points now. So 2 to the right, 1 up, 1, comma 0, 0, comma negative 1, and negative 2, negative 2. And then you can see when I connect these points with linear pieces, what I've just graphed is my inverse function, f of x. So here we are asked to find the inverse of f of x, which equals 4x plus 2. Then we're supposed to graph the original function, the inverse function, as well as the line y equals x. So what we're going to do algebraically to find the inverse is we start by writing the function in terms of y. So we're going to, instead of f of x, we'll just call it y equals 4x plus 2. Now because we want the inverse, we want to switch the input and the output. So we will switch the x and the y in this equation. Now we're going to solve for y by subtracting 2 to both sides. And to solve for y, we're going to divide each of the terms in this equation by 4. And we'll just rewrite it because this is a linear function. We'll put it in slope-intercept form. So the inverse of the original function will be 1/4 x minus 1/2. Now graphically, we'll start by graphing the original function. The y-intercept is 2, the slope is 4, and we'll connect those dots. There is my function f of x. Now graphically, we can graph this inverse by switching. You see these two points that lie on the curve f? Let's just switch the x and the y. So the y-intercept, right, was 0, comma 2. Let's graph 2, comma 0. The other point that lies on this curve, negative 1, comma negative 2. Let's switch those inputs and outputs and do negative 2, negative 1. So here is my function f inverse of x. And in fact, when I graph the line y equals x, I notice that the function f and the inverse f inverse of x, these are reflections across the line y equals x.